Okay, all right. So today we're going to be talking about, we're going to go into a brief stoichiometry chemistry review. We're going to kind of go into basic stoichiometry, okay? So this is like honors, regular chem, general. We're going to kind of go into a general review of stoichiometry and how it's actually, how it's used, okay? So the way this works is actually interesting. Stoichiometry, basically what we're doing here, don't overthink it. It sounds like a powerful word when you first think about it. But really, we're just using chemical reactions, right? We're using chemical reactions that we already have, and we're basically taking the material of one and finding how much material can either be produced or how much material is in an element, or in a compound or a molecule. We can find how much of that matter or material of hydrogen or oxygen, for instance, is in H2O. Okay, so there's many different reactions we could do here, but we're basically going to primarily use chemical reactions with stoichiometry. We could use titrations. We could do all sorts of things. We could produce the outcome, how much material will be produced, or how much product will be produced, rather, not material. We could also determine how much reactants will be produced in a reverse reaction. So it's very interesting how this works. Okay, so first we're obviously going to balance our chemical equations, because this is where you get to, this is the fun stuff. This is where you get to use your chemical equations or your chemical reactions and actually put them to test, right? So you get to balance them first. It's like putting it all together. So we write out and balance, and then we're going to note the coefficients, okay? So the way I like to do this is a simple flow chart, okay? And I like to look at this flow chart. I don't want to confuse anybody, but the way I like to look at this flow chart is right here. This is the key to stoichiometry, okay? And obviously when we add volume and molarity, it's going to change, but this is the most basic that we're going to use for general stoichiometry. So this is our flow chart right here. We're going to go mass to moles, right? You're going to use the mole ratio, which is really just the coefficient ratio. So you could also just say coefficient. The coefficient ratio, okay? And then we're going to go to mass of B. So we go from A to A, and then we go from A to B ratio, and then we get B, okay? Well, we convert moles, which gets us mass, right? So the way this really generally works is we have mass in grams. If I look at my materials, right? I have mass. Then I'm going to say, okay, now I'm going to find moles, right? So this is the dimensional analysis way of canceling this out. And then we go from moles. So I like to write it as grams of, and we'll do this in different colors so this makes more sense. We start with grams of A, right? We have A still A. Moles of A. Now we're going to do a B, okay? We're going to do a B now, okay? Moles of B, okay? Then we're going to say moles of B once again equals mass of B. Okay, so look at that. Now if I go through, right, I'm going to take a green pen and go through this. If I go through, look how everything cancels. Grams cancels grams, A cancels A, moles cancels moles, A cancels A, moles cancels moles, B cancels B. I'm left with mass of B, which is what I want, right? So look how that works. Isn't that interesting, right? So that's stoichiometry for you. This is the basics. As long as you know this flow chart, you're going to get through it. Because if I just give you moles, right? If I give you moles, I just eliminate this piece. I say, okay, moles, coefficient ratio, moles to mass, right? And then if I just give you, if I want to go from mole to mole, I'm just going to do a mole to mole ratio, right? Right, and then if I want to go from mass to moles, I'm literally just going to do this, right? So there's different things I could do. I could cut out certain sections of this to get to certain pieces, not the center, obviously, but I could cut out the ends, the middles, both ends, and I could find something, for instance. So let's start with a small... Actually, let's just start with moles of something, okay? So let's just convert moles, okay? So for instance, let's say I have the chemical reaction. This is the most basic one I'm going to pick. I'm going to pick a basic chemical reaction. Or if this is even a chemical reaction, this is just the formation of water, let's just say. So we have H2 plus O2 goes to H2O. Now I'm going to balance this out because this is diatomic because of Hunkelbrief. I have two hydrogens over here, which simply means that I have to put... I need two oxygens. I simply have to put a 2 to get those two oxygens. Now I have 4 hydrogens, so I have to put a 2 there. Okay, now it's balanced, right? 2 oxygens, 4 hydrogens, 4 hydrogens. Okay, so we're balanced. So we're balanced our chemical equation, okay? Now what we're going to do is we wrote it out. We're going to note the coefficients. We have 2, 1, 2, okay? You can always just put your 1 there, whatever. Okay, so if I'm given 0.2 moles of H2, maybe I want to find how many moles of H2O are produced. And then maybe I want to find also how many moles of O2 are needed to create this many moles with this, okay, to react all the O2, or to 0.2, right? And that's limiting reactant stuff, excess reactant. We'll get to that at a different time in a different video. But I just want to show the basics here of how we're going to convert to find this, okay? So if I want to find how many moles of this is needed and how many moles of this is needed, I'm going to use the mole ratios, okay? The moles ratios. And this is very simple, okay? Literally what I could do is I'm literally just setting up a proportion, right? We did proportions in math before, where we say moles over coefficient equals moles over coefficient. And you can write it either way, coefficient on the top, coefficient, right? Because you're gonna cross multiply anyway, okay? And you're just going to set them equal to one another. Okay, and I like to write it as over coefficient, right? Because it makes more sense to me that I take the coefficient. So I literally have, and in this case, I could actually write this out. Okay, I could say moles of H2 over the coefficient of H2, right? And then I want to find the moles of O2, right? And I have the coefficient of O2. So what I'm solving for really is this, okay? And I'm given all these, okay? So I'm simply going to put 0.2 moles of H2 over 2 coefficient of H2 equals, right, equals my coefficient now of O2, which is 1 coefficient, right? So it's simply, what this is basically going to do is it's just going to divide it by half, right? So I'm literally just taking 0.1 and I'm dividing it. I'm basically taking 0.1 and dividing it by 2, and it's a very simple problem here, okay? So literally it's just, or 0.2 and dividing it, so it's literally just going to get me 0.1 moles, okay, of O2 are needed, okay? So that's how this one works, all right? Now if I want to solve for H2O, guess what? I would do the same thing, right? So, and as you see here, H2 is here, H2 is here, these cancel, right? I have O2, and I'm solving for O2, okay? So I solve for moles of O2. Now guess what? If I wanted to solve for H2O now, it's literally just going to be what I write in green now. It's going to be H2O, and I'm just going to have 2 coefficient. Well, guess what? 2 over 2 is 1, so it's literally 0.2 moles of H2, 0.1 moles of O2, okay? Because I'm literally taking ratios here. It's very, very basic in this regard, okay? But now if I pick it up a bit, right, and I move into simply a little bit harder problem. Let's do another chemical reaction, okay? Let's do this kind of chemical. That wasn't really a chemical reaction. That was more of a formation of H2O, hydrolysis, or that wouldn't have been hydrolysis. That would have been the reverse of hydrolysis. That was combining, creating H2O, creating water. So that would have been quite the opposite of hydrolysis in that regard, okay? So basically what we're going to go through here is we're going to say we have silicone. Let's do silicone dioxide, okay? So silicone, that pen is old. Let's get a new pen. Silicone dioxide. Okay, so silicone dioxide plus, and let's react that with hydrogen fluoride, okay? So I'm going to react that with hydrogen fluoride, and I'm going to get silicone tetrafluoride, right, plus H2O, okay? And you can write the states of matter, but in this case, we really don't need that. It's good. It's a good practice to write it out, okay? But you really don't need to in this situation, okay? So, because it's just going to get crazy with, But I basically can write all that out. So basically what we have here is, now hydrogen fluoride is actually an acid, right? Because there's a hydrogen attached to it, right? So I know this is acidic, hydrogen fluoride, okay? And it's going to react with silicon dioxide. We get silicon tetrafluoride, H2O. So let's balance this equation out. So on this side of the equation, right, I'm basically going to need, now what I would like to balance out first is the oxygens, okay? Because I have 2 oxygens on this side and 1 on this side. So I'm going to have to put a 2 out front of this H2O. Now I got 4 hydrogens, and I also need 4 fluorines. So look at that. That works nice. I just do that. I just simply put my 4 out front. Now we're all balanced, right? So let's check. Is everything here balanced? And yes, it is. 4 hydrogens, 2 oxygens, 2 oxygens, 1 silicone, 1 silicone. Everything's balanced, right? All right, so basically in this case, we balanced our equation. Okay, so that's good. Now we're going to move into is, let's say I'm given 2 moles of each here. Now I'm going to have excess reactant in this case. But let's just say, actually, let's just do this. Let's say we have 2 moles of silicon fluoride, or silicon dioxide, sorry, not fluoride. So I have 2 moles of silicon dioxide. Oh my goodness. Okay, and now let's say I want to find how much silicon tetrafluoride will be produced, okay? Now let's just say I want to find that because guess what? I want to know what the mass is of this. Let's say I'm making this in abundance, okay? Because in industry, you might be wanting to make something in abundance, and you want to find how much reactant is required to perform a product. Okay, to form a product. It's very good for efficiency, obviously, right? Because you want product. You don't want to waste any product, right? You want to put in the same that you'll get out, and you want to know how much will be produced in that reaction, or what will be produced in that reaction. So I have silicon tetrafluoride. I have 2 moles. So clearly there's 2 moles of silicon tetrafluoride, right? Because it's a 1-to-1 coefficient ratio. Whereas I would divide this one by 4, divide this by 2 to get moles, okay? But I'm going to take this through the process, okay? So I'm going to start with my given. I always start with my given. It makes the most sense to start with your given. And so the reason why is because what else are you going to start with, right? So I have 2 moles. 2 moles of silicon dioxide. I like to write it out just like that, okay? 2 moles of silicon dioxide. Now what I want to do is I want to convert this to mass. So if I look at my flow chart that I made earlier, I'm already given moles, so guess what? I could get rid of mass. I don't need to worry about mass. So I'm literally given moles of A. I'm going to do my ratio, and I'm going to wind up with a mass in the end, okay? So I'm just skipping one step, okay? So I'm given moles. Now I'm going to do my ratio, okay? So you could either write it as moles to mole ratio or coefficient, right? You could write it like I did it. I think the easiest thing is to do coefficient to coefficient because this gets confusing with those moles, right? But the thing is, like, if you do coefficient to coefficient, it's fine too because they're literally going to cancel. This whole piece cancels, right? So I'm going to say this many moles of silicon dioxide, right? I have 2 moles of silicon dioxide. I have 1 coefficient of silicon dioxide, 1 coefficient of silicon fluoride, and I want to be left with silicon fluoride. So now dioxide's gone, okay? I have silicon fluoride. Now I'm going to take my molar mass of silicon fluoride, okay? Or silicon tetrafluoride. Sorry, I keep saying that wrong. The correct nomenclature is clearly silicon tetrafluoride. Okay, so silicon tetrafluoride. If you find your molar mass, you can do that on your periodic table. But I'm just going to say what the molar mass is. The molar mass of silicon tetrafluoride is 104.08. Okay, so 104.08 grams per mole of silicon tetrafluoride. Let's write that there. Okay. So look at this. Moles from all the way over there cancels moles from all the way over here. Silicon tetrafluoride cancels to silicon tetrafluoride. I'm left with what I want, right? Now if I plug this into my calculator, I'm simply going to get 2 moles times 1 divided by 1, the same thing. So I'm literally just going to multiply it by 104.08. 104.08. And I'm simply going to get 208.16 grams of silicon tetrafluoride. So that's the mass of silicon tetrafluoride I'm going to get from 2 moles of silicon dioxide. Okay. And so it's very interesting as you look at this. You can see your ratios, okay? So this is moles to mass, right? So I go from mole to coefficient ratio to mass, okay? And I like to repeat these in my head to myself. It makes more sense to repeat them to yourself. You go from moles to coefficient to mass, or mole mass you could call this. This is a mole mass problem. Okay, so if you really want to write it out as mole mass, you can. Okay, the last one was just a mole problem, so this was just a simple mole to mole problem. And now we could do a mass to mass problem, if you wish, or we could do mass to moles, right, to moles. So you could do mass to moles to moles. The only difference by doing this is you're just adding mass in before moles, right? So I find the moles of silicon tetrafluoride. I was already given that, though. If I were given mass of silicon tetrafluoride and I wanted to find how many moles, for instance, I would simply have, over here I would have mass, right? And then these two would cancel of silicon tetrafluoride, or silicon dioxide in this case. Okay, and then my molar mass of silicon dioxide would cancel with this. I get the number of moles, I do my coefficient ratio, and so on and so forth. I wouldn't know my number of moles, so I wouldn't have 2 here. It would just be grams to moles, coefficient ratio, moles cancels moles, I get mass. Okay, so I really don't have to do a mass to mass problem because this explains how to do it. I just took this extra step out of the flow chart. Some of them that confuse people, though, is mass. For some reason, this confuses people. If we get mass and we're given moles to moles, and it's a little bit more confusing because we end with the coefficient ratio in this case. So all I'm doing is knocking this part off. So if I wanted to find mass to moles, right? Mass to moles, right? So if I'm given, let's draw a line here, and I want to find mass to mole, that's literally just saying, okay, that's literally saying if I had 20 grams of silicon dioxide, right, I'm going to find my moles of silicon dioxide, right? This all cancels out, right? And this is my grams of silicon dioxide. So I have 20 grams, that cancels, okay? Silicon dioxide cancels. This one didn't cancel yet, but it will here. Right, and now I'm going to do my coefficient of silicon dioxide. Now it cancels. My coefficient, and now this is the reason why this gets confusing, because some people don't, this is why I say to write out the material for each one. Because what happens is people do not write out what they're canceling, and this is where they get confused. Some people will put silicon dioxide on the top, put this here, and that's wrong, obviously, because you're trying to cancel silicon dioxide. See how everything nicely cancels? Silicon dioxide cancels here. Silicon dioxide cancels here. So therefore, the coefficient of silicon dioxide must go on the bottom, which is 1 coefficient. But in this case, it wouldn't matter anyways. You're doing a 1-to-1. But if I wanted to find H2O, let's say I wanted to find the mass of, or the moles of H2O, well, yeah, then I'm going to say 2 coefficient of H2O, and that's where it will matter, and that's where it will affect you. And then you could say moles per gram of H2O, grams per mole, and then this would be your molar mass of H2O, which is 16 for oxygen. I believe it's about 18, right, if I remember correctly. So it's 18.014 maybe grams per mole, if I remember correctly, off the periodic table. So regardless, the point is moles will cancel with, and there's H2O. So I wind up with grams of H2O, which is what I wanted. This all cancels out. Everything cancels. Okay, that's the only thing. You just got to make sure you set this up on each side of the bar for dimensional analysis properly. Okay, and it will get a little more confusing when we get into volume, but for now this is just a simple mass to moles ratios and everything, and hopefully this all makes sense. So I'm hoping this helps. The best thing to do is to look at this flow chart. Okay, just memorize the flow chart, memorize the process. Mass to moles to moles to mass. That's all you really have to know. Mass to moles to coefficient to mass, you could say instead. You could replace moles with coefficient ratio. Okay, so you could say mass to moles to coefficient ratio to mass, or however you want to say it. But just make sure that the coefficient ratio is the third thing in line. Okay, because if you flip it, you'll notice that it won't cancel correctly because you're going to be putting your coefficient ratio and you're going to be canceling. It's not going to work properly. You're going to be canceling moles from the other material, the other reactant, which is not what you want to do. Okay, so you're always going to go from mass of A to moles of A, and then do your ratio, and then eat your mass. So any part I take out, which this is the last one I just did, mass to moles to mole ratio, right? You could do this in any sort of way. Moles to, obviously, mass to moles, right, of the same material. Moles to a different material, and then mass of that different material, right? Or I could do moles to mass again, right? Or I could do moles to moles as well. I could just do my ratio, right? So there's different formats here that you could do, but this is just a basic introduction, so I hope this helped. Thank you for watching.